That liquid is boiling away there, even though it's unimaginably cold. In fact, this is the only material which remains liquid at such low temperatures. It's liquefied helium gas. And its temperature is within a few degrees of the lowest possible temperature, absolute zero. I've come to the Clarendon Laboratory here in Oxford, which is one of the world's leading low-temperature research laboratories, because there are some remarkable properties of helium that we want to look at today. And it's going to turn out that these properties can be interpreted in terms of the counting procedures that we're going to discuss in this course. Well, let's start off by seeing what happens when we reduce the temperature still lower. Quite suddenly, the boiling ceases. What is happening is that there's a sudden transition from one phase of the liquid to another. It's similar to what happens when water changes into ice. But in this case, both states are liquid, and the change in properties is even more startling. For example, the bubbling has stopped because the heat conductivity has shot up 1,000,000-fold instantaneously. What is even more remarkable is that this liquid exhibits the amazing property of being without viscosity. Inside this small container, we have some helium held in by a very finely porous plug. Above the transition temperature, the helium is viscous and it can't pass through. But as we cool the helium below the transition temperature, we can see that the liquid suddenly penetrates the holes of the porous plug. It's become a superfluid helium. Now, how can we start to explain why helium behaves in this remarkable way?
Well, surprisingly, the behavior of liquid helium is all tied up with the way we count atoms. And that's because of the way they're distributed. In this program, we're going to look at the various ways of distributing atoms, and one of them will give us the model we need to explain the behavior of helium. So let's start off with a few basic facts about counting. It applies whether we're counting atoms or, say, snooker balls. Now, I'm going to be interested in the number of ways of distributing a given number of snooker balls among a given number of pigeonholes like these. Now, you may remember there's a very strong connection between distribution problems and selection problems. When I distribute the snooker balls, I have to choose which pigeonholes to put them in. And you'll also remember that there are basically 4 types of selection problem, depending on whether the selection is ordered or unordered, and whether or not repetition is allowed. So you won't be at all surprised to learn that there are basically 4 types of distribution problem. Let's look at them in turn. I'm going to assume that I have 5 pigeonholes, and I'm going to distribute 3 objects among them. And first of all, I'm going to assume that these 3 objects are distinguishable. That means we can tell them apart, like these differently coloured balls. Well, let's put the first one in here, and the second one in here, and the third one, we'll put that with the red one in here. The question is, how many ways are there of doing this? Well, there are 5 possible positions for the first ball, 5 for the second, and of course, 5 for the third, giving us a total of 5 times 5 times 5, which is 125. And in general, if we have n pigeonholes and k balls, then the total number of ways is n times n times n k times, and that's just n to the k. So the number of ways in this case is just n to the k. Let's see what happens now if we allow only 1 ball in each pigeonhole. In this case, the first ball can go into any of the 5 pigeonholes, the second can go into any of the remaining 4, and the third can go into any of the remaining 3, giving a total of 5 times 4 times 3 ways. That's 60, which is less than half the number we had before. And in general, if we have n pigeonholes and k balls, then the number is n times n minus 1 times n minus 2, right down to n minus k plus 1. And we call that n sub k. It's equal to n factorial over n minus k factorial. So the answer is just n sub k. And that deals with the cases where the balls are distinguishable. Let's now see what happens if the balls are the same colour. They're indistinguishable. And we'll deal with the case where there's just one ball in each pigeonhole, like this. How many ways can this be done? It's just the way of choosing 3 pigeonholes out of 5. And that's just the binomial coefficient, 5 choose 3. That's equal to 5 factorial over 3 factorial, 2 factorial, which is 10. And in general, if there are n pigeonholes and k balls, then the answer is the binomial coefficient n choose k. And that's equal to n factorial over k factorial n minus k factorial. So the answer is just n choose k. And finally, let's see what happens if we have 3 balls of the same colour, but we can put more than one in each pigeonhole, like this. How many ways can this be done? Well, this involves a bit of a trick, so let's see how it goes. We can think of this arrangement as a sequence of partitions and balls. 4 partitions and 3 balls. But the balls look a bit like zeros, and the partitions look a bit like ones. And so we get the symbol 1, 0, 0, 1, 1, 1, 0. And similarly, if we'd started with this arrangement, we get the sequence 0, 1, 0, 1, 1, 0, 1. Now you'll notice that in each case there are 3 zeros corresponding to the 3 balls and 4 ones corresponding to the 4 partitions. So the problem is really that of taking 7 symbols, that's the zeros and ones, and choosing just 3 of them to be 0. And this can be done in 7 choose 3 ways, that is 35 ways. And if there are n pigeonholes and k balls, then we're choosing k zeros from n plus k minus 1 symbols, and the answer in this case is n plus k minus 1 choose k, which is n plus k minus 1 factorial over k factorial n minus 1 factorial. So the answer is just this binomial coefficient. So that's the 4 types of distribution problem. Just one of these is the correct model for the helium problem, and the question is, which one is it? We can't tell directly from the mathematics. We've got to go back to the physics.
What's all this counting got to do with the helium problem that we started off with? Well, it's a surprising fact, but the behavior of a physical system depends on the number of different possible arrangements that we can put the system into. For example, if I call W the number of possible different arrangements, then I can define a quantity S, which is proportional by a factor of proportionality K to the log of W. Now, K is a famous constant called Boltzmann's constant, and S is called the entropy. And it turns out that a physical system always behaves in such a way as to make the entropy have its maximum value. Furthermore, it appears that the universe is evolving in such a way as to always increase the value of this entropy S. Now, you can illustrate this in the following way. You see, S somehow measures the amount of disorder in the system. Now, if I take a pack of cards, which I've ordered very carefully into suits, for example, I have ace, king, queen, jack, 10 of spades, and so on, all very neat. If I take the cards back and I shuffle the pack really well, and now I put the cards out again, you see, I've destroyed the order, I've increased the disorder in the pack. So what you can say is, I've increased the entropy. Well, what really concerns us for the helium problem is the fact that for a physical system where we have a number of different possible arrangements, the arrangement that is chosen in practice by nature is the one that makes S have its greatest value. Well, what's this got to do with our specific problem of helium? Well, that depends on how we count helium atoms. More specifically, on how we distribute helium atoms among their energy levels. You see, we believe that helium atoms obey the laws of quantum mechanics. And according to quantum mechanics, the atoms can only distribute themselves among various energy levels. And it's these energy levels which are analogous to Robin's pigeonholes. Well, let me show you what I mean. You can think of energy levels as being like this set of steps. Now, in a system which consists of many atoms, like helium, then the atoms have to distribute themselves among the various energy levels. For example, high temperatures correspond to high energies, so there'll be more atoms up here, and low temperatures correspond to low energies, so there'll be more atoms down there. But exactly how do the atoms distribute themselves among the various energy levels? Well, that's exactly analogous to the way Robin arranged his snooker balls in the various pigeonholes. Now, that means that in general, there are going to be several different ways of distributing the atoms among the various energy levels, depending on whether the atoms are distinguishable or indistinguishable, and as whether we can have just one atom per energy level or several atoms per energy level. Well, it turns out that in practice, atoms always behave as if they're indistinguishable. So that only leaves two cases, case C and case D. Now, case C, well, that's a model due to the physicists Fermi and Dirac. That's the case where we're allowed only one atom per energy level. Well, what does that look like in terms of our steps analogy? Well, that's just equivalent to a set of steps like these, which are just wide enough to accommodate one person per step. So in the Fermi-Dirac case, we have at most one atom per energy level. And Robin's already calculated the number of arrangements in that case. It's just n choose k. Now, in case D, which is a model due to the physicists Bose and Einstein, the atoms are again indistinguishable, but several atoms are allowed to occupy the same energy level. That's like the original set of steps, where several indistinguishable people can occupy each step. So in the Bose-Einstein case, we have a set of energy levels like these, where several atoms can occupy each level. And we've seen that the number of ways of distributing them is just the binomial coefficient, n plus k minus 1, choose k. Now, let's evaluate the entropy in each of these two cases. So, the formula is S equals k log W. That means in the Fermi-Dirac case, we're going to get the entropy S equals k log n, choose k. And in the Bose-Einstein case, we're going to get the entropy S equals k log n plus k minus 1, choose k. Well, which of these two expressions will give us the correct behavior of liquid helium? In order to see that, we need to evaluate these expressions more explicitly.
Well, k log n choose k is equal to k log n factorial over k factorial n minus k factorial. And we can expand this log term to give k times log of n factorial minus log of k factorial minus log of n minus k factorial. And now let's do the same sort of thing for the Bose-Einstein case. S is equal to k log W, where W is this binomial coefficient. We have k log of n plus k minus 1 choose k is equal to k log of all of this. And again, we can split the log up. We have k times log of n plus k minus 1 factorial minus log of k factorial minus log of n minus 1 factorial. So these are the results that we've got. They don't really look very meaningful at first sight, but you'll notice one thing: they all involve the logarithms of factorials. So if we want to make any sense of these, we've got to know what the log of n factorial looks like. Well, if we write n factorial as 1 times 2 times 3 up to n, and then take logs, we have a sum of log terms. We can represent these terms graphically by means of a bar chart. So log 1 equals 0, log 2 is represented by this bar, log 3 by this one, and so on, right up to log n. The sum of all these terms is the sum of the areas of all these bars. And if n is very large, this total area is approximately equal to the area under this curve, y equals log x. This sum is given by the integral of log x from 1 to n. And that turns out to be n log n minus n plus 1. Well, for large values of n, we can ignore the 1. So log n factorial is approximately equal to n log n minus n. Well, before we use this expression, I'd just like to show you another way of getting it. You may remember that Stirling's formula gives us a very good approximation for n factorial. Namely, n factorial is approximately square root of 2 pi n times n over e to the n. So the log of n factorial is approximately log of root 2 pi plus log of root n plus n times log of n over e. Well, the first of these terms is about 0.919, and the second is a half log n, and the third one is n into log n minus 1. Now, the first two of these terms are very small compared with the last one, so we're going to ignore them. What does that give us? Log of n factorial is approximately n log n minus n. So now we've got this approximation, let's substitute it back into these expressions for the entropy. And we'll start with the Fermi-Dirac case. Log of n factorial, that's just n log n minus n. Log of k factorial, k log k minus k, and similarly for the last term. And we can do the same sort of thing for the Bose-Einstein case. But first of all, we're just going to make one more approximation. You see, n is very large, and so we can ignore the 1 in comparison to it. And similarly, we can ignore this 1 in comparison with this n. So let's see what this becomes. The first term becomes n plus k log n plus k minus n plus k. The second one, of course, is k log k minus k. And the third one is n log n minus n, because we've ignored the 1 again. So we now have these expressions for the entropy in the two cases. And as you can see, they're still quite complicated, but in principle, if we know n and k, then we can calculate s in both cases. The question now is how we set about choosing which of these two models is the right one for the helium problem. And to answer this, we've got to go back to the physics.
Well, how can we use Robin's expressions to illuminate the physics? Well, it's not easy as they stand. You see, the expressions are rather complicated, and we have to determine when the entropy S is a maximum. And that's not easy to see from complicated expressions, but it's much easier if you draw graphs. And that's what I've done here. I've plotted a graph of the entropy S in the Fermi-Dirac case as a function of the number of particles K per energy level N. So this expression is just the density of particles per energy level, and the graph in the Fermi-Dirac case looks something like this. Well, in the Bose-Einstein case, I've done the same thing. This is the graph of entropy S versus density of particles, and this is what the graph looks like. And you see that the two graphs are very different in each of the two cases. Well, what does this tell us about the physics? First of all, the law is that we must look for the value of S to be a maximum. And that clearly occurs in the Fermi-Dirac case about here. That's the density of particles per energy level about a half. That's about 50% probability of an energy level being occupied. Whereas in the Bose-Einstein case, we find that the entropy gets more and more according as the density of particles gets greater and greater. So in this case, the particles all have a tendency to congregate in one energy level. In terms of our step analogy, Bose-Einstein condensation looks something like this. everybody ends up on the ground level. Now, that phenomenon of condensing in one energy level is called condensation. And it's this property of condensation which is crucial to the explanation of the properties of liquid helium. Well, why should that be? Because all the particles, all the atoms, tend to condense in one energy level, that means that they're sharing a common motion. Now, because they have this shared common motion, that means it's very difficult to disturb that motion. So the particles tend not to be viscous. They're superfluid. Well, that's a very crude explanation. It's not the whole story. The whole story is complicated enough to warrant the attention of researchers in laboratories like this all over the world. But still, I hope that in this program, we've introduced you to some of the remarkable properties of helium. In fact, there are other, even more remarkable properties, and that we've shown you that there is an intimate relationship between these properties and the way we count.